Yeah, Mark's presentation then? Yes. Okay, cool.
All right. Welcome back, everybody. So, our first speaker for the AGN session will be Mark Bongolo, who is one of our AKU students, and he worked with me 2 years ago on this object, feral CO3, which is a long-term variability behavior of the Netherlands Super Galaxy feral CO3. And if we get started over there, the share. Oh, yes, okay. Thank you. And then we just have to go and manage this from over here. So welcome back, everybody. Hope you had a good short break. And we will have another longer break at 4. Okay. If you're good to go, take it away.
So, hi everybody. I'm Emmerich from Northern Kentucky University. Here's Dr. Grupa, my mentor. And like he said, today I'll be presenting my research on the long-term X-ray variability in narrow line Cepheid 1 galaxy 40303. So here's the agenda for today. At the beginning, it will just be about general information. So I'll just give you guys the need to know. I won't go into much details in order to spend more time on the analysis itself, the reasoning behind what we did and why we did it. So yeah, so what is an AGN? So an active galaxy nucleus is a supermassive black hole at the center of a galaxy worth millions, if not billions of solar masses. For example, the one that I studied is worth 2 million solar masses. One of the defining characteristics is its accretion disk and its accretion rate, the rate at which it converts matter into energy. So surrounding materials spiral inward, converting gravitational energy to radiation. So basically you have materials in the vicinity of the black hole and other materials far in the gravitational potential. So as they spiral, then there's friction due to the viscosity of the gas. So the speed reduces, and when the speed reduces, they lose angular momentum and spiral inward because they get pulled by gravity and get accreted. They have extreme luminosity, can actually host galaxy by a factor of 100 to 1,000. They have multi-wavelength emission, kind of similar to a black body. So here's the structure. So an agent has two emission region. The broadline region, so this is where the gas cloud sits kind of in the vicinity of the black hole. So they're deep inside the gravitational well. So the orbital velocity is like super high. It's like in the order of thousands kilometers per second. And the narrow line region sits far deep in the gravitational potential. So they have much lesser orbital velocity in the order of hundreds of kilometers per second. So yeah, narrow line Cepheid 1 galaxies. And again, don't get misled by the name. It's not because it's called narrow line, it means that's that broadline region. Actually, the narrow line just means the broadline region is narrower than the typical AGN. So they're characterized by narrow H-beta emission lines. So we get the velocity of the broadline region material from the width of the emission line. So since it's narrow compared to, for example, a broadline Cepheid 1, which is a typical Cepheid 1, we can infer that they have low orbital velocity in the broadline region, low orbital velocity and the radius is comparable to the typical broadline Cepheid 1. So we can deduce that the mass has to be small. And since the luminosity of the narrow line Cepheid 1 is the same as the one of the broadline Cepheid 1, it means the accretion rate is the same. So it got to mean that the fractional mass growth rate of the narrow line Cepheid 1 is much, much bigger for the narrow line Cepheid 1 than the broadline Cepheid 1. So this is SWIFT, the satellite that I used for this data. It was launched in November 2004. It got 3 telescopes, a gamma ray, an X-ray one, and a UVOT one. The one that I used for this study is this one. So yeah, 40303, the AGN data studied. As you can see, we got a narrow width indicator of the narrow line Cepheid 1 galaxy that it is. It was discovered during the Orosa All-Sky survey. So it was a survey conducted from 1990 to 1991, where it referenced a bunch of highly variable active galactic nuclei. So we started monitoring it in 2008. So we crunched 40 observations to make this analysis. So the key event we noticed an increase is X-ray flux. So to make you guys understand this graph, I'm gonna have to give you guys a little bit of preamble, and I'm sorry if you already know all that. I'm just gonna give it for the people that might not know. So first off, how does the agent get its luminosity? So luminosity comes from the accretion rate. So the equation for luminosity is efficiency times accretion rate times c squared. So it means that, for example, if the source purely gets brighter or fainter, it got to come from the accretion rate. So what else? Yeah, so when the accretion rate increases, the disk gets harder, the temperature increase. In fact, like the temperature of the accretion rate is proportional to a fourth of the fourth root of the accretion rate. So it's mathematically small, but physically it's quite significant. So we know, for example, from Stefan Boltzmann that harder objects produce more energy. This law also tells us that the emitted peak wavelength of the black body radiation spectrum shifts inversely with temperature. So it means harder object, the peak wavelength shifts to lower wavelength, so higher energy, higher frequency. Now, the swift soft X-ray band is from 0.3 kiloelectrovolt to 1 kiloelectrovolt. The hard one is from 1 to 10. Now, when the disk heats up, the black body spectrum shifts to lower wavelength, right? So it's pushing more photons into the soft X-ray band. And it's pushing more photons into the soft X-ray band because the spectrum is moving into the direction of the low X-ray range, okay? So because of that, the soft count rate, the volume of soft photons you're receiving is growing faster than the volume of hard photons you're receiving, while the overall count rate is increasing. So when you look at here, this is the equation of the hardness ratio is hard minus soft divided by hard plus soft. So because of that, since the soft count rate is going up faster than the hard count rate, this will be negative. So the hardness ratio will become more negative. And you can see the most poignant example is like right here, for example. You can see a sharp increase in count rate and a sharp decrease in hardness ratio. This, for example, is indicative of a change in accretion rate. So these two events, for example, the fact that this emits more energy, more photons, and at the same time, the hardness ratio is sharply decreasing, is what's being referred to as softer when brighter. The softer just means you're pushing more soft X-ray photons into the X-ray band. So the source is moving to the low X-ray range. Brighter just means it's more luminous. And we know that specifically because of this anti-correlation I was telling you about. As the count rate increases, hardness ratio decreases. And this correlation is certified by the Spearman rank correlation right there. So a -1 indicates that the hardness ratio is decreasing while the count rate is going up. And again, key result, negative correlation. When the source becomes brighter, the hardness ratio decreases, the source becomes softer. So why is all this relevant? So this really tells us, it helps us deduce because of the variability. For example, if you had an absorption event, it's like a gas cloud coming and blocking the X-ray, you would expect the source to get harder while getting fainter because the gas cloud preferentially blocks the soft X-rays, and it's only the hard X-rays that have enough energy to go through the gas cloud and reach the sunlight. So you have a overall decrease in count rate because you have less soft X-ray coming, but at the same time you have the hard photons are coming more than the soft photons. So your hardness ratio gets more positive while the count rate is decreasing. This is not what we observed. If you're like a reflection, X-ray getting reflected and reprocessed by the disk, you would have the source getting harder while getting brighter, meaning that the count rate would go up because you get more hard photons, and the hardness ratio will also go up. So this would give you a positive Spearman correlation coefficient. This is not what happened. So to summarize, the accretion rate increases. This leads to an increase in the disk temperature. The black body spectrum shifts to lower wavelength, higher energy. So the hardness ratio decreases, and this confirms that the variability was due to a change in accretion rate. Summary, so again, Ferrol 202 is a narrow line CFL1 galaxy identified by the narrow H beta line, which communicates low velocity in the orbital broadline regions. So they got a relatively small black hole mass. Swift has been monitoring it for 18 years, 40 observational we analyzed. The event that happened for the X-ray flux was softer when brightest, negative Spearman correlation coefficient. And yeah, the variability of softer when brighter trend is consistent with change in accretion rate, not absorption or reflection. For the future, we hope to continue monitor Ferrol, perform possibly a UVOT analysis, and trigger XMM and new star. Yeah, thank you guys.
You can come with this project. Because the story is, Mark, he thought was an engineering physics student, but now he cannot graduate in engineering physics thanks to the Department of Homeland Security. And now he has to graduate in physics, which he needed to graduate. He quickly needed a project again. So I said, okay, catch up with this one again. That's also the reason why we don't have new data of Feral CL3, because Swift is right now in hibernation. Any other questions?
Yeah.
Yes.
Is this relationship between the something that's being other galaxies as well?
Yeah, it's not specific to Pearl. Say Pearl is another common. Yeah, this relationship, this anti-correlation specifically is equal to the change in accretion rate, a pure change in accretion rate. And yeah, so again, the experimental correlation coefficient is really what we because it only at the concrete versus the atmospheric graph. We can get tricked between like, is it a reflection or is it a change in accretion rate? And this negative correlation, this negative coefficient. So no, it's not a unique thing for all the other celebration.
Okay. All right. Thank you, Mark. Hey, I hope this works with a little microphone here, and then hopefully this thing works, right? I hope so. All right. So our next speaker is myself, and I will be talking about IC 3599, which is a galaxy that I have studied, or I should say an AGN that I have studied over more than 35 years. I kind of have a personal relationship to this one because that's the reason why it's on the license, on my license plate. When you see my car out there, yes, it's not red anymore. That was my old car. I have a Prius now, which is more dark, but it's still on there. And this was the first author paper that I ever published in 1995. So that's the relation here. So I have followed this object since more than 35 years. Came out of the Rosette-O Sky Survey, was one of the brightest sources during the Rosette-O Sky Survey. Have a picture here, which shows you know what? I can probably use the mouse here. And then the people online can see this, as well. So what you're seeing down here on the x-axis, I hope the online people can see this, is the Rosette-O Sky Survey count rate that Mark introduced, was done between 1990 and 1991. And this is the pointed observation that we took years later. When you look at the line over here, this solid line, that means there's no change. This means a factor of 10 fainter. This means a factor of 10 brighter. And this means a factor of 100 lower. And IC 599 was one of these galaxies that dropped by factors of almost 100. When we followed this galaxy later on, we found it was even dropping by more than 100. These were pointed observations then back in the 1990s. And the question was, of course, what happened at the time? What happened when we saw IC 3599 doing the outburst? That's the low state spectrum, the optical spectrum. That's from the Sloan Digital Sky Survey. And it shows a normal low luminosity CFAT 1.5 galaxy, 1.9 galaxy. 1.9, because my colleague Stefan Ikomosa in Germany discovered there was a little bit of a broad emission component in H alpha. I always said, what, maybe not. More like a CFAT 2 galaxy, but okay, CFAT 1.9. But this was in 2000, and the SDSS spectrum was from 2007, I believe. I have to look this up again. This spectrum, however, was the spectrum that was published basically right after the Rosette-O Sky Survey. At the same time, while I was working on this paper, also Neil Brunt, who is now at Penn State, he was a PhD student in Cambridge, was working with Ken Pounds at the time. They did a survey in the wide field camera with Rosette, which was this additional EUV camera on top of Rosette, and they found this as one of their very bright sources. So they followed this up, took a spectrum half a year after the Rosette-O Sky Survey, and what you see is these lines, the spectrum looks dramatically different. This is H beta. This is not O3. This is H beta. O3 are these tiny little lines over here. And then you see also these very strong coronal ion lines, like ion 14, like ion 10 over here, ion 11. Very impressive spectrum The resolution was unfortunately pretty low. The noise was pretty high. These are spectra that I took at McDonald Observatory years after that. And you can see how these lines really decayed. And this became more and more again a CFAT 2 galaxy or a CFAT 1.9 galaxy. Now, one of the hints was that these lines were coming from hydrogen and helium. And those are, of course, lines that you see from a main sequence star. So the idea might have was in the 1990s, well, at least one of the ideas that what we are looking at is a tidal disruption of a star. So when the star gets too close to a supermassive black hole, if it's not too big, then the star can be disrupted by the tidal forces of the star. And we see for a moment this object re-brightening very strongly. There's a little bit of an artist rendition of what this is supposed to look like. That's all cool. And we all thought this is a great explanation. This is a wonderful explanation. The only problem with this is an active galactic nucleus. So it has an accretion disk. And when it has an accretion disk, you cannot exclude other reasons for other explanations for having a flare like this, because the other flare explanation would be an accretion disk event, would be an instability in the accretion disk itself. And bingo, we saw another outburst in 2010. Now you can still argue, well, this might be, you know, some partial tidal disruption event where a star in an orbit goes by every 20 or so years, and you will see another flare. That was actually proposed by a group in Italy by Sergio Campana, who was actually saying this was this data point over here, which was done by Chandra in 2002, was also a flare. So he predicted after every 10 years there should be a tidal disruption event coming by. And when we followed this object by Swift starting in 2013, the prediction was, well, it should happen in 2019, but nothing happened. So we could exclude definitely that kind of scenario. We still said, well, we expect another outburst or flare by something like maybe 2030. Because you cannot really 100% predict when this happens. That was the prediction. And guess what happened? Last year, we went into sun constraint in August, but when Swift observed it again, when IC 3599 came out of the sun constraint by Halloween last year, it was bright. It was bright by a factor of about 50 compared to the pre-flare emission that we saw here. So these are this is the XRT count rate. This is the UV emission, and you can see there's maybe some hint already there before the sun constraint that the source became slightly brighter. And it significantly increased in the UV as well as in X-rays. That's the follow-up that we had immediately. So once this started, once I saw this source was in this very bright state, I immediately triggered Swift with daily observations. I also put in a request for director's discretionary time for XMM, which I thought, you know what, let's risk it, let's go for it, and I get it approved. Funny story with that is that over the last something like 10 years, I had an XMM proposal, got always approved for a TOO trigger that if the source ever becomes bright again, I can trigger XMM and I get observations with XMM. Well, unfortunately, in 2024, the panel decided, well, they will never trigger this thing and denied the proposal. And well, guess what? We triggered it. So fortunately, because of that, I got the discretionary time on XMM, which is this line over here. This is when we did the XMM observation. That was in December 9th and 10th. The green lines here are Lick observations that were done because we also get through Stephanie Comosso. She had some connections to Lick Observatory, so we got some Lick spectroscopy, and I will show you the results in a second. The red one here is from my previous student, Salem, who is currently in Göttingen. In Göttingen, they have an observatory class where they go to Asiago in Italy and do observations with a 1.2 meter telescope. Pretty cool. So she did some spectroscopy with this. This is the XMM observation. This is the XMM-PN count rate. And what blew me off was really these almost quasi periodic oscillations that we see in the EPIC PN light curve. This definitely needs some further analysis, which I'm working on right now. We'll start pretty soon on this because we are still in the process of resubmitting the paper, our paper number 1. The paper number 1 is on the flare, is on the flare that we saw in October or November. I have to resubmit the paper by next week. So hopefully it gets approved by the end of next week or something like that. So then it gets published. So you should see this paper pretty soon. When I run a Lomskargel periodogram, you see that we see variations, and pretty clear actually, in 26,000 seconds and also secondary peak at 17,000 seconds. One caveat with this is our observing length was not very long, so we only get 4 periods, so it's a little bit iffy. So what I need to do at the end of the day with those data is running something like Monte Carlo simulations in order to figure this out. This is the new spectrum. This is our new spectrum that we got. The black curve here is the spectrum from LIC from November last year, and you can see this is H beta. This is O3. Spectrum changed dramatically. This is ion 14. This is ion 10. You can see, we see the corona lines again. The spectrum reacts in the same way. We saw it 30 years ago. So it is pretty exciting. So this is Neil Brand spectrum from 1991, published in 1995. And this is our new spectrum. And you can see really the similarities between these two objects. That's, by the way, the spectrum that Salem took. Salem graduated from NKU in May last year, and is now a student in Göttingen, where I got my PhD, where, sorry, the observatory is 30 years older than this one. Gauss was the first director. Yep. But she took this as part of her observing class, put something like 3 hours of observing time into it. Pretty nice spectrum, actually. It's I thought this was really cool. So she picked this at the object because in previous years I had her doing also the Swift observations and follow-up observations. She gives talk here, many times. So what causes this? Well, we are pretty convinced that this is radiation pressure instability. So the old model that we produced before still fits. A caveat with this is we don't know what the rise time was when it went into outburst, because it came out of sun constraint and it was already bright. We do not know what it is doing right now, and I get to this in my last slide, because Swift stopped observing this science operation at the beginning of February. And the reason for this is drag force. I get to this in a second. So we want to continue monitoring, of course. And then, of course, we have a bunch of papers coming out. So paper 1 is the first one. The revised version should be submitted very soon. Optical spectroscopy is in preparation by Stephanie. That should be also coming out sometime this year. And then the XMM paper will be paper number 3. But what happens to Swift? When one of the big surprises when I was on the senior review last year was that Swift may be falling sometime this year into the Pacific. And it will not be, you want to have it fall into the Pacific, not like what we see this evening, hopefully successfully. It is something that we do not want. The reason is Swift is a low Earth orbit satellite, which means it reacts to drag forces. And typically, you don't have to worry too much about it, but yes, you do, because like with the International Space Station, you usually have to put it out to a higher orbit again. Now, Swift has no active drive. The only way Swift works is by reaction wheels. So what can we do? So the problem also was, some of you may have enjoyed the Aurora Borealis, right? Looks great. The problem with that is you heat up the atmosphere. Simple physics question, what happens if you heat up a gas? It expands, right? So the atmosphere expands, which also means your density of the atmosphere becomes higher in a higher orbit, which then means you slow down your satellite even more, which means you lower your orbit more and more and more, which means eventually it will fall into the Pacific. And right now, the prediction at the beginning of the year was that Swift has a 10% chance that it falls in the Pacific by June. So what to do? NASA agreed to send a mission up there, which is coming from a company that is called Catalyst. They will send a mission up there coupled to Swift and then boost it up to 500 kilometers again. You will say, well, what is so difficult about this? This has been done in geostationary orbits all the time. Well, in the geostationary orbits, guess what? You don't have an atmosphere. You don't have to worry about drag forces. But if you have to worry about drag forces, you cannot really predict what happens when you do this mission. The other thing is Swift has absolutely no equipment that can where you can lock on another spacecraft. It's not built for that. So they had to figure this out, what grabber arms they do, lock onto Swift and then boost it. So this will be launched on June 1st and then gets to the space station, not to the space station, gets to Swift, hopefully by something like July 1st, July 4th or so on. So 250th anniversary, we have probably the boost of Swift. And then it will take a month or two to bring it in the higher orbit. So hopefully Swift will be working again by the end of the year. So we can continue with observing the sources, like, for example, IC 3599, or of course, Feral 303. Thank you very much. All right, questions? I do what? Oh, good point. I have no idea. See, we should check that. It's May 31st. Okay, so they bumped it up by a day. Awesome. That's good. Thanks for checking. Do we have any other questions, remarks? Maybe from, yes, Jesse.
So you had flagged that there's some oscillatory features in the thoughts on what's that?
Which one do you mean when you talk about the data?
Yeah.
The oscillations? Yeah, I really have to look into that. I was very surprised about this because, I was expecting, some variations, but something like that we see these quasi periodic oscillations that you see from some of the even tidal disruption events was very surprising. Typically, they are longer. They are not just within a few hours. They are usually within days. So seeing something like this was really unusual. Good question. Yes? Oh, it is because it goes up by factors of something like 100 or 200, right? So it is really, it's not just a flare and it stays, it's just a short-term event. It is really an outburst, which means it stays there for a while. But we don't know how long it will stay there because, again, right now we are flying in the blind. Okay. Thank you. Our next speaker is Trevor. And Trevor is also, believe it or not, kind of a student of mine because he was part of the Oaks program, the NSF Oaks program at Louisville. And I became his mentor. And Trevor will talk about XMM observations. We'll talk about what McKinley mentioned before. So the short-term variability of AGN, how this links to properties like the black hole mass. So I think can we? Yes? Yes? Okay. All right. You tell me. Okay. Oh, yes. Stop sharing here. And then we should be good to go, right? We leave it like that. Okay. Take it away. Yes. Cool. Yeah. Oh, that's weird. Okay. Awesome.
All right.
Oh, I'm sorry. I still have the microphone.
Okay, can you guys hear me? Okay, so I'm currently a graduate student at U of L. I just started this semester actually. So my work with Dr. Group Day was during after I graduated from undergrad. I did like a post-bac with the Oaks program. But now I'm working on something else. But I did want to give a talk over the data we had together and the results we found with XMM. So today I'm talking about assessing short-term variability with XMM across 54 AGN that we found. So I'm going to give a brief introduction to AGN. You're probably going to hear this a bunch of times in this session, but a brief introduction to AGN. What are active galactic nuclei, or AGN? So they're extremely luminous. It's an extremely luminous region in the center of a galaxy, and so this region is powered by accretion of matter and dust and gas onto a black hole. And this brightness or luminosity of this AGN can vary on timescales from hours to years. And this is like a simulation. At the top right there is like a simulation of like some variable source. It's not an actual source. So I just want to show it as an example of like what variability could look like. But so for my project, we use XMM. How do we observe this? So we use XMM, and XMM basically collects the X-ray photons into into the telescopes of the actual satellite or the telescope system, optical system. And these photons are actually converted using the CCD into actual measurements that we can use for data analysis and stuff. And so to actually measure this variability of the AGN, this XMM typically observes from 10 to 100 kiloseconds, which is about 3 to 30 hours. It depends on the source and like the time and like whatever proposal gets made for some source and wherever the observation is made. But yeah, so we can, over this time scale, we can measure the actual variability. And to do this, there's 2 different ways you could do this. Typically, with Swift and UVOT data, you use fractional variability. So this is good for Gaussian distributions, which like the Swift data gives you some good like Gaussian distribution and matches. You can use like the mean for the variability. But what Dr. Grupe found in his 2024 paper that X-ray photons with like XMM X-ray variability works better with the medium value. So it's the X-ray fluxes are not typically an actual Gaussian, so they're usually non-Gaussian. So this p-var value actually works better for the X-ray and XMM. And these are the equations for it on the screen there. And so we can use these variability measurements and compare it with properties such as black hole mass and also the Eddington ratio for these galaxies. So the Eddington ratio is the luminosity, the volumetric luminosity over the Eddington luminosity. And I did that through my project. And so the motivations for my project were to do this with XMM Newton and do a comparison with Swift data, but I never actually got to the point where we compared it with Swift data. But we had the same sources from Swift and XMM, and we're actually looking at the short-term variability in XMM, and we want to measure that variability and understand the processes that drive active galactic nuclei. And so for my sample selection, there was 128 sources in the Swift GI program. About 54 of those sources were in XMM Newton. A total of 239 observations were made for these 54 sources. And so here on the bottom left here is an example of what like a source looks like when you get the data and you put it into a program. And then on the right here is the different the Swift and XMM. So when I did this sample selection, I got a big table of sources. I also had to get the source properties for each of these sources. And so I did that I got the redshifts, I got the hydrogen column density, and I got the mass black hole. So the redshifts were obtained from Dr. Grupe's paper, because a lot of these were in his paper as well, because there's the same sources as Swift measured. And also got some of the redshifts that were not in the paper from Simbab. I got the hydrogen column density, which is needed for the spectral modeling. I got it from SAS using the RA index. So you basically just input the RA index of the source, and it gives you this column density. And I did that for each of the sources. And the mass black hole was also obtained from the 2010 paper that Dr. Grupe released. Most of them were in that paper, but a lot of them were also not in that paper. So I had to use some equations from his 2004 paper that I don't put on this slide here because it's not the main focus of the talk. But I used that and I got the black hole mass for that. And so here's an example of some of the sources we have. So IRAS, the Farrell 1116, and NGC 4593, and you have all the different RA deck, redshift, hydrogen column density, and the mass of the black hole. So with these sources, I measured the variability. So I have some examples on this slide here. So for example, on the left here, we have NGC 4051, and I have the variability parameters at the bottom. So you can see on the left that the variability of the NGC 4051 is highly variable. So it's 0.5 for the FVAR and 0.652 for the PVAR. And then we have a MKN 766 on the right here, and you can see this source is not very variable in XMM at least. And this is the time scales on the bottom here. So from on the left here, it's from 0 to 120 kiloseconds. So that's about at the beginning is like 10 to 100 kiloseconds. So it's about 30 hours, I think. And then this on the right is about a few hours, not upwards to 30 hours there. And so I did this for each of the sources, but I also did some spectral fitting for these sources as well. So I fit all the sources using XSpec and some basic spectral fitting parameters there. And so I calculated the flux from the continuum, and then the X-ray luminosity was computed from the flux and redshift. And so when I did all that, I got this this graph on the right here. So you have the counts and you have the energy on the actual x-axis, and counts on the y-axis. And then you have the data here, and then the fit of the data there. And the bottom graph there is actually the ratio between the model and the actual data itself. You can see that it fits fairly well. There's some points where it's not. There's some dips, but overall it kind of fits very well. And then the luminosity, I calculated in the bottom left using the bolometric luminosity for the Houston editing ratio was using the calculation in the bottom left. The Dr. Group A called log LBB. And so after I did this, I did this for all my sources, and I actually measured the variability for all the sources, and I compared it to the variability in the mass of the black hole. So for FBAR, for my correlation analysis, you can see some very strong anti-correlation of sources. Some of the sources have very large error bars, but this might be because using FBAR on these X-ray sources, it probably doesn't model them super well, and so there's some high error bars for that. But you can see that we have some from two different tests of correlation coefficients. We have the highly negative correlations, and the p-value is also very small. So these are actual things we're actually seeing. I did this for p-var as well. You can see our error bars are much smaller, and it shows basically the same result, albeit at a little higher of anti-correlation for both tests. So I also did this for the Eddington ratio, but unfortunately, we didn't really see any strong correlation between these values. So there's the correlation coefficient test shows some slight correlations, some slight positive correlation, but the p-value is above the null hypothesis value. So it's just actually probably no correlation here. And it's the same story for the p-var as well. So even with the better constrained error bars, we still see the same result. There's basically no correlation that we can see at this point. If I were to continue this project, maybe we could do some other tests and see if there's any other correlations with the fractional variabilities. But for my project, this is where I ended. So here are my conclusions. So there's a strong anti-correlation between AGN variability and black hole mass. There's no significant correlation that we found for variability in Eddington ratio. In these next steps, there's not what I will be doing. This is what probably an undergrad will be doing with Dr. Group A. Probably improving the spectral fits because it can probably be improved a little bit. So check correlation with luminosity. Also investigate whether these correlations change with different AGN classes. But yeah, that is my talk. If you guys have any questions, please. Be easy on me. I haven't worked on this project in a while. So.
Well, yes, and we have to look probably at what we said about the relation with the Eddington ratio.
Yes.
Just realized was by making this
yeah, there's like two groups there.
Maybe.
Maybe.
I mean, we have to maybe look at why this is maybe one group on highlights and one galaxy because it solves this with other correlations as well that you can separate them out.
Yeah.
So we probably also go multi-dimensional.
Yeah, I never got that far in my project, but that will be something to do in the future.
That's fair. Grace and another dimension. So yeah, great talk. Any other questions? Okay. Then Trevor, thank you very much.
All right.
There is another old student of mine who was an old student of mine because they have only for a year, and that's Bruno Connelly, who will be talking about a highly polarized source, which is iron 1239 plus 333, which was also a bright source during the highly polarized, which you do not see on typically in an extragalactic event. Typically, you see about 1%, less than 1%. This one is what, up to 4%, 5%?
Yes.
Quite unusual. So, Brennan, it's all yours.
Your audio is coming through something.
Okay, great.
Okay, there we go. Hello, my name is Bryn Connolly. I'm currently a senior at the University of Louisville. As Dr. Gruber mentioned, I was a student under him in the Oaks program last year, and this is my project that I worked on with another AGN. I know we've talked a lot about different variability with AGN, and this is an example of a source that is not very exciting in terms of variability, but it is exciting for other reasons. So this is high polarization in NLS1 galaxy Iris 1239.7 plus 3333. Gotcha. Okay, so I know you've heard plenty of context on what an AGN is. A lot of the context in general will have been in some of the prior ones, but I'll just reiterate a little bit. So my project specifically is looking into the unified model of AGN. So this is the idea that we have many different categories of AGN. As you've heard Mark talk about, we have narrow-line Seyfert-1 galaxy, which also happens to be the category that I'm looking into. But we also have Seyfert-2s, quasars, many other different categories. And the unified model is proposing that these aren't actually all different types of AGN. We are just sort of seeing them through different angles or different obscurities or things like that. So that is kind of what this project is broader, looking at it in a more broad sense. So as I said, Seyfert-1, Seyfert-2s, narrow-line Seyfert-1s. So luckily, Mark explained a little bit about the difference between a narrow-line Seyfert-1 and a normal Seyfert-1. So a Seyfert-1 has broad and narrow-line regions. A Seyfert-2 does not display broad-line regions, and a narrow-line Seyfert-1 displays relatively narrow broadline regions. So for instance, this is the spectrum of my source. And then we're also going to talk a little about polarization. And this is important here. If you remember, polarization is just when light goes from a three-dimensional wave to a two-dimensional wave. This is important here because it can occur through scattering, reflection, many things like that. And it actually applies really well to Seyfert galaxies because Seyfert-2 galaxies can appear to be Seyfert-1 galaxies when polarized. So as we were talking about with that unified model, since we're talking about different ways to sort of see how these could all be the same types of AGN, this is one way that really intrigues us of how does polarization affect how we categorize these galaxies. And we also see that there is higher scattering at higher frequencies of light. So for instance, as I just mentioned, we can see that Seyfert-2 galaxies, such as the one at the top here, can appear as a Seyfert-1 spectrum when polarized. So this is my galaxy. This is Iris 1239. It is a narrow-line Seyfert-1 galaxy. Technically, it's a Seyfert 1.5, but we're going to call it for right now, for our purposes, narrow-line Seyfert-1. It's been monitored since 2005. We have about 25 observations, and there's no real notable variability here. This is our Swift observations, which we have, if you remember, seeing like what Mark had or Dr. Grupa had. So if it isn't variable in any way, why is it significant? So we're going to talk about, as I just mentioned, its polarization. So it has this relatively high polarization for an NLS1 galaxy. And if you can see, it's going to be the triangle here. It only gets up to around 8% polarization at its highest. And, oh, sorry, it's the circle, my bad. And it has an average of about 5% polarization, which doesn't sound very high. However, this is quite high for a Seyfert galaxy and for AGN in general. We usually see about less than 1% on most of these AGN. So we're asking, okay, we see all this polarization, what does it actually mean? What does it amount to? So in order to investigate this, we're going to use a couple of different data sources. People have talked about Swift quite a bit. that actually wasn't our main source for this one. We just used it initially to check if there was variability. And we also used it to get sort of our initial light curve on it, but that didn't show us too much because Swift is great for long-term variability projects. You can very easily get data. However, it doesn't give the most in-depth look at things. So that's why we switched over to XMM, which Trevor talked a little about, and NewStar. NewStar is very similar to XMM in that we get this high detailed X-ray data. The only difference is that XMM covers from 0 to 12 keV, whereas NewStar covers from, I believe it's 3 to like 70 keV. So putting them together, we get the full range of the spectrum. Also, one thing to talk about is with XMM, I think Trevor talked about a bit about the PN camera, which functions very similarly to the XRT camera on Swift. But we also used the RGS, or the reflection graded spectrometers. So these can give us even more detail on our observations. However, they do have a little bit of an issue, as you'll see coming up, in that they have been hit by micrometeorites, so they are missing 2 of their sensors. So the data looks a little bit wonky with that. Luckily, the software that we have has been altered. So with these observations, we started, making our spectra and trying to fit them with different models. So our first model that we tried was a power law model, and this did not fit, which is actually a good thing, because a power law model would have implied, okay, there's nothing wrong with this, it's just a very normal narrow line C41 galaxy. And we knew from the polarization that that was not the case. So this was just kind of our sanity check to make sure we weren't going on a wild goose chase. The next model we tried a partial covering absorber, because this would have implied, maybe there was some sort of, like, as it says in the name, partial covering. So this would have given us still our soft X-rays, which we see in this source, without, it would have had some sort of, object to obscure and scatter the light without hardening the X-rays. So we liked this as an idea more than just a normal ionized absorber, because you would think that an ionized absorber would likely harden more of those X-rays. However, this model didn't fit super well, so we moved on to try just an ionized absorber, which, even though we didn't think it would work as well, it did work a little bit better. It still was not overall great. So from here, we were just kind of wondering, okay, well, what possible model could fit here, and also what is causing all of this polarization. So we went to dig a little deeper, and this is when we started using the RGS data. So the RGS data does show a ionized absorber model, but it shows a more complex one. We see an oxygen edge and some emission lines, and when we take the model that we used with the RGS data and put it back in the PN data, it shows us a better fit for the PN data as well. And this is what I was talking about here with this RGS data. Those 2 dips in the data are where the micrometeorites have hit those sensors. So they get a little wonky, but the overall model is still helpful for us. So for our next steps, we hope to continue working with and refining the RGS data. We hope to keep looking into other wavelengths. I mentioned the UV here, but it could also be useful to look into the infrared. We want to complete the SED for this source. Potentially, we would like to complete an international polarimetry explorer proposal, since it is a good candidate for that because it's so bright, and we obviously already know that there is polarization. And currently, we are working on writing up a paper to, put all our results together and spread them out. Thank you. Any questions?
Yeah, you will continue working on this,
yes,
as we discussed. Great.
Yeah, thank you. When was NewStar launched? It's a little newer than Newton. It's newer than XMM.
It's newer than XMM. It's 2012.
Okay.
Interesting thing about NewStar is it was launched from an aircraft. They had a Pegasus rocket underneath it, so they flew it actually 60 kilometers, dropped the rocket, and then launched it. Which means, and it unfolds, once it was in it's still working great. I mean, it has some, as you heard, with the micrometeoroids, but most of the issues it can run for the next 10 years.
Yeah.
At least. So, given that Athena is not coming online, given that, you know, who knows what happens to Chandra in the next couple of years, we still have a powerful observatory out there. Anything else? Yes.
What are those regions where you said they were affected by the micrometeorite? I see that there's still like lines, still the.
What happens there is you have three audience.
The inclusive would still use those like energy regions, or
Yes, you
it's
can.
not just max out.
Because what happens is XLM has two RGSs. One got hit at this one. This is RGS1, this is RGS2, where the dip is. So they have 7 different detectors, 7 different CCDs. One got hit is out on that detector, and the other one is out on the other detector. So when you combine them, this is why you see this drop not to 0. This is why there's still some signal.
That's why on the other.
Yes, correct. They also lost a CCD in one of the MOS cameras each, but it also has 6, 7 CCDs. Fortunately, it's not the central one, because it's the central one you're screwed. If it's one of the side ones, it's okay. If you study point sources like EGN, it doesn't matter. Anything else? Thank you, Brun.
Thank you.
All right. You want to be a little You're ready. All right. Okay. So our next speaker is going to have from Holy State, who will continue on analyzing the
I wouldn't have laughed at 6'7", but then Wes laughed at it and looked straight at me when he did.
Like I said, they give them a trick on the question, just make it a strike.
Good job answering that question.
Oh, yeah, this is my favorite thing about presenting with our group. I'll never answer a question ever.
But I said, I came to this point of the freshest possible, thank you, the freshest possible presentation, because I'm literally still. Should be sharing it now. Then I've got it as an extended screen, so.
So are you in the Zoom? Are you in the Zoom?
Probably not. How does it do that? How does it do that?
There's a link in the email.
Okay, hold on. I saw you sent an email this morning. Okay. If I could just get to my emails. Here we go. Wait, that's the Google Drive.
It should, if you scroll down, I think it's not hard to say.
Hold on a second here.
Yay!
All right, show me where's
There it is.
that.
And guess what? You are left.
We'll just move that all back out there then. Okay. Joining and there I am. Okay, so as long as I've joined, then now share. Desktop 2.
Yeah.
Okay. Looks like oh, and I'm muted here, so let's unmute. So it's going through this here? Got it. Okay, so what I was saying is that y'all are getting the freshest possible presentation because I'm still working on the analysis. So this is as new as it can possibly get. In fact, we only got, this is a project that Filippo Domando in Italy and I are doing through the Hubble Space Telescope. And we have been doing a Hubble snapshot program of this particular class of galaxy, which has not been studied. The host galaxies of these have not been studied at very high resolution much yet. In general, let's see, where's our pointy stick? Oh, this is longer now. All right. In general, these are narrow line Seyfert 1 galaxies. So as we've been talking in this session before, active galaxies have a central black hole surrounded by accretion disk and all these other things here. And I'll show that same diagram in just a moment. Seyfert galaxies in general are kind of like a low-powered quasar. And they are an unobscured, we're looking at a subtype of those that are the type 1s, that's unobscured. The narrow line Seyfert 1s have relatively narrow Balmer lines, so hydrogen alpha, beta, and so on like that. A weak oxygen 3 emission and strong iron emission then. The weak oxygen, strong iron means that they are unlikely to be obscured. Some would say that they are unobscured. But then the narrow Balmer lines indicate small black holes, as I'll show in a minute. And interestingly, well, the key thing is that only 7% of this class are radio loud. So if we recognize that Meg Urey and Paolo Padovani diagram from back now 31 years ago, just realizing that, we have here the central black hole surrounded by the accretion disk. Whirlpool of gas falls in, glows brightly. That's what makes the bright spot of light in the center. And the important thing for this is that the little black dots around here, I'm sorry, the little gray speckles around here are the clouds that are orbiting that black hole. Ultraviolet light from the hot accretion disk illuminates those clouds, and then it bumps their electrons up, they fall back down, and you get strong Balmer lines. Those Balmer lines then are very broad because the gravitational pull of the black hole moves these broad line clouds around very fast. And that just gives us Doppler broadening. They're moving towards you, they're blue shifted, away from you, red shifted, and that all blends together to give very broad lines. Farther away here, we have these clouds that are farther out. They have narrow emission lines because they're moving more slowly because they're farther away. We get a combination of these then. We can see here, this is a spectrum of of an earlier sample I'd used, where you can see the hydrogen alpha and hydrogen beta, Balmer lines there are broader, and then your oxygen 3 and some of these others here are quite narrow. So the thing is that because of the gravitational pull on the broad line clouds, the width of those lines is related to the mass of the black hole. Got to do some other correlations, but that is a way of measuring the black hole mass. So the narrow line Seyfert 1s have, by being selected to have narrow Balmer lines, we're selecting for relatively small central black holes. They're still supermassive, but they're on the small end of that there. All right. The other thing is that nearly all of the galaxies that these narrow line Seyfert 1s are in that have been studied at high resolution have been found to be in spirals, which is interesting here. Well, it actually makes a lot of sense. The black hole mass has been found to be proportional to the galaxy's central bulge. So in the spiral galaxy, of course, you have your bulge and your disk. In the elliptical galaxy, the whole thing has the same dynamics as a bulge. It's all bulge there, which means that generally your elliptical galaxies will have larger central black holes than your spiral galaxies because the bulges are just smaller in those. So this means that with the narrow line Seyfert 1s, by selecting for the narrow Balmer lines, that selects for the smaller black holes, which you would think would select for spiral hosts. And at low redshift, that's really what we see. But 7% of these are radio loud. So what about these here? The thing is that you can get radio emission in some different ways, but there are a number of these radio loud narrow line Seyfert 1s that show characteristics of relativistic jets. Plasma jets, near light speed jets coming out, just like a radio loud quasar, in fact, particularly like blazars. And in a few of these, which I'm not really going to talk about in detail because we're looking at a larger set right now, about 24 of them have been found with gamma ray emission. And this is a key way of saying that these at least do have relativistic emission because we're getting inverse Compton scattering off the jet. We get gamma rays there. So the thing is that these jets are usually associated with elliptical galaxies, rarely in spirals, although there are exceptions. They've got different formation, thick and thin accretion disks, which I won't go into. Cold gas in spirals can help quench the jets, even if they were produced to begin with. And there are, again, some exceptions to that. So while nearly all those narrow line Sievert ones that are radial quiet are in spirals, we expect the jets to be in elliptical hosts. But do these radial loud narrow line Sievert ones, do their host galaxies really look like what we've seen out of the radial quiets, the majority? This I'm actually going to skip here, but we'll come back to that if there are any questions on it. So our observing program, because these radial louds have not been studied at high resolution. A friend of mine who's been on some of my other papers, a couple of 3 years ago, got the Nordic Observing Telescope. Oh, boy, I forgot the acronym now. It's like NOT. Nordic Optical. Oh, thank you. So he got he got a number of these radial louds there, and was seeing a mix of things here. We're using the Hubble Space Telescope. We proposed 105 radial loud narrow line Sievert ones, which we're saying is the parent population of these gamma ray emitters. We use the Hubble Snapshot program with the Wide Field Camera 3 in the infrared mode. And they tell you, you might get about a third of your observing list in the snapshot program. We actually got 57, which feels pretty good. 44 were good results. And so let's take a look and see what we got. Okay, so it turns out we've got 13 of these. And I thought for a while that they'd accidentally sent us some bubble chamber tracks from a particle accelerator. This is actually the Hubble failed to get guide star lock in 13 cases. I have never seen this before in any of my other observing programs, but there were 13 of these. Maybe it's snapshot programs because you're not on the target very long, but I don't know. So anyway, we got 44 that were usable. And indeed, we've got several ellipticals. Clear case here. This last week, I've been doing a very early preliminary analysis to take a look at the isotope shapes here and to make a radial profile plot that would give me a quick look to see whether it's really elliptical or just a very, very smooth spiral. And all of these here do show up very clearly as ellipticals. Interesting cases on this, you can see a shell structure around there and in the outer part here as well, indicating some past merger activity. Some of these may be at the centers of groups or fossil clusters even. That one also, as smooth and as compact as that is, it shows a clear radial profile of an elliptical. A bit of extended emission on this side again, showing some interactions. More extended emission around in this here, probably with some companions, a few like that, but again, an elliptical shape for it there. Even these compact ones are showing that up. We've got a range of redshifts going from less than 0.1, about 0.1, 0.2, all the way up to over a redshift of 0.5. So this is spanning the range of the narrow line Sievert ones that I think have been found so far. We've got 13 ellipticals that appear to the eye to be elliptical, and so far all the ones I've examined show that. For the spirals, that one is a very clear spiral. So I was originally excited at the possibility of finding any ellipticals at all, because that just doesn't show up for the most part at these low redshifts. But now I'm maybe even a little more excited to find the spirals, because we have clear radial emission from these, probably jetted, most of these cases. And in a lot of these, the spiral pattern is absolutely clear. Some of these are bulge dominated, looking from the profiles there, the previous one and this one as well. But they're still showing the clear spiral shape. A few of these also with a probable bar. So a galactic bar is one method which gas can be funneled down to the center of the galaxy where it can accrete onto the black hole. So the presence of bars is going to be interesting to investigate here. Also, the fact that a lot of these spirals have appear to have companions that they're interacting with, and so the spiral arms may be tidally formed or at least enhanced. This one is heavily interacting, but still has a notable spiral shape. Same here. This one was a little tough to make out. There is the appearance of a bit of arm starting off left and right on that, but it comes out with a pretty clear exponential disk decay law on that there. Same thing with this one, a very tightly wound one, possibly a bar in the middle, but we'll see once I do a full two-dimensional model for it. And then we've got about another dozen or so that are interacting. I'm only going to show one of these cases, but where we have, let's see, our host galaxy is this one here. So we've got an interaction with another galaxy up there, long tidal arm stretching out. And I'm going to make a guess, because we don't have any other redshifts on the other members nearby. I'm going to guess that we've got a group here with several of these then, just based on the appearance and the size. But we've got extended emission all through this, coming out here, all along like that. So it's probably at the center of an interacting group. That's one possible trigger for an active galaxy, but not the only kind of a case then. It's going to be interesting to compare these to quasars, where what triggers a quasar has been debated for a long time, the idea of interactions being the thing that triggers a quasar, but it's actually been found that those happen less often than we'd originally thought. In this case here, it seems to be about a third or so, but they may be a little bit more, depending on how we classify it. So an interesting pattern is emerging between Marco Bertone's paper from 2023, where he took a large look with the Nordic Optical Telescope. He was finding a mix of ellipticals and spirals. We're finding with the radial louds now the same kind of a thing, mix of ellipticals and spirals, while the radial quiets are almost exclusively spiral. On the other hand, quasars are the other way around. Radial quiets are a mix of elliptical and spiral, while the radial louds are almost exclusively elliptical. And so what we're finding so far, out of those that I've modeled, we've got 12 ellipticals, 9 spirals, and 17 interacting, and then a whole lot of others that are kind of ambiguous there. All right. Oh, sorry, one last point, 2 last points. The redshift distribution. The gamma ray emitting ones here, I've scaled them up by a lot. If we look at how they're distributed in redshift, they make a larger and larger fraction of all known narrow line Seyfert ones as you get to higher redshifts. So we're probably looking at some kind of an evolution here, and the radial labs may be showing that as well. Maybe that's why we see these differences with the quasars. Next thing to do then, two-dimensional decompositions of these, and ways of measuring the black hole masses independently of the broad lines, including the bulge mass and the correlations it has with the Sirsic index, will give us a better look and to see whether these really are small black holes, even in the radial loud cases. Thanks.
Thank you, Tim. Yes, Carol.
The color bar, you said?
Yeah.
This is this is simply, I took a shot from the DS9 image viewer. And so it's just showing, what you're saying about what the color bar is showing? Yeah, so it's just the brightness here. So this is, well, bright is bright on this here then. This is with a logarithmic scaling and the heat color map, which does even a little more logarithmicness to it there. So it compresses that dynamic range quite a bit.
Tim, I have a question for you.
Yeah.
You have the Netherlands, radio loud Netherlands of one galaxy in the sound of that back in 2011 with
Luigi Foschini, yeah. Probably some of these then, because I've worked with Luigi on a bunch of these, and I've got to look and see what the target list was back in 2011. But there may be some overlap, but I haven't checked that yet.
Yeah, I would say that it's great to check because we can look at the
yes.
those ones we know for sure that that is
Right, and this is actually from Luigi's paper there, where he was pointing out that these gamma ray emitting narrow line Seyfert ones seem to make a counterpart to the neutron star emission there. So just this whole dynamics of jet production at large scales and then down at small scales then, these may be kind of the missing link to that. All right.
Any other questions? Before we leave, we will take a photo. You will do the announcement? Yeah.
Okay.
Actually, a couple of requests real quick. Can I grab your mic?
Yeah.
I will be stopping the recording.
So yes, we would like a group photo, and we'd like to have out on the steps of the observatory, hopefully before it starts to rain or spring.